Okay. So far we discussed about linear differential equation models. So let me start on that point. One of the linear differential equation models that we discuss is half-life and carbon dating. So if you look at the differential equation that I have written here, which is same as half-life and carbon dating, right? In half-life and carbon dating, we had capital A. Remember the amount of substance that is left. But if you replace that A by P, this is the same differential equation model, same initial value problem, same solution. Now here capital P stands for population. Population after some time T. K is a constant, which is the growth and decay rate. Now P naught is the initial population. This is a linear differential equation model and we call it the Malthusian model. Now I'm talking about what I have written in blue color. Okay, this is the Malthusian model. Now according to this model, the population grows exponentially fast. Now think about this. This term is an exponential term. So if you draw the exponential graph of exponential function, the graph goes to infinity when time goes on, right? If you draw y is equal to e to the x. Now what does that mean physically in terms of population? The population will grow infinitely over time. Now think about that. Can it happen? We have lack of resources, fight for food, fight for shelter. Okay, so population will never become infinite. It will never grow infinitely, right? Think about rabbit population in a jungle. If the rabbit population is high in a jungle, predators will come and eat. Think about a city, your living city. If the population is too much, over 1 million, people will leave the city. Where do people live? Where the apartments, houses come, right? So there are fight for survival, fight for resources. This Malthusian model does not take that into account. So this model is not a reasonable representation of population growth. Okay, so that is why we need a new model. Now that is where we are going to discuss about nonlinear differential equation model. So this we call this differential equation here is called the logistic growth model, which is a nonlinear differential equation model. Why it's nonlinear? Let's simplify the right hand side. If you distribute those brackets, we get simple kp minus simple kp square over capital K. We have a p square, right? Isn't p dependent variable? Yeah, and if it is linear, shouldn't we have degree 1 for p? We should, right? So we have degree 2, so this is probably a nonlinear differential equation, which is the case. Okay, so this is nonlinear differential equation. Let's learn about this. P is the population after certain time t. Simple t is of course time. So we have two k's here, uppercase k and lowercase k. Excuse me, the lowercase k is the growth and decay rate. Okay, so which is same thing that we have learned before. Capital K, we call it the carrying capacity. Carrying capacity means the capacity or the number of species that a certain environment can hold. Okay, what does that mean? Let's take a city. The city might, let's take a simple city, New York. Let's say New York have only resources for 1 million people, nothing more than that. If you have more than 1 million people, people will leave the New York City. If you have less than 1 million people, well, you can sell your properties to new people and you can invite people to come and live. But not more than 1 million. 1 million is the capacity that New York can hold. So that's the same. Okay, let's take a quick example and understand it again. But one thing, we have two constants here in the beginning of the question. Carrying capacity is a constant, growth and decay rate is a constant. In most of the problem, when you're dealing with a problem, you will know the carrying capacity beforehand. Okay, so the question description should give you the carrying capacity. Okay, let's look at an example and understand it. So look at this example. 10 grizzly bears were introduced to the park 10 years ago. Okay, there are 23 bears in the park at the present time. The park can support a maximum of 100 bears. That is the carrying capacity, right? The park can only have 100 bears, nothing more than that. Okay, if you have less than 100 bears, of course, which is the case, the number of bears will increase, but not beyond carrying capacity, right? Okay, so that's an example. Now, let's analyze the differential equation first before we try to solve it. Trying to solve it is a longer process, which is a case for another video. Okay, but let's analyze the differential equation. Analyzing means we were really interested about equilibrium solutions. So how do we find equilibrium solutions? Well, we make the rate of change equal to 0, dp over dt equal to 0, the right hand side equal to 0, and we solve for, dependent variable. We solve for p. If we look at the right hand side, p is equal to 0 is the equilibrium solution, right? If you substitute 0 for p, you will get right hand side as 0. Good. Then if you substitute p to be k, if p is capital K, we have 1 minus capital K over capital K. Capital K cancel out, 1 minus 1, which is 0, so we will get 0. So these two are equilibrium solutions of this differential equation. Now, what is the meaning of this, physical meaning of this equilibrium solution? dp over dt being 0 means rate of change of population is 0. Rate of change of population is 0 means there will be no change of the population. So when you approach p is equal to 0, p is equal to k, there will be no change of the population. Which does make sense, right? If you have a 0 population in the beginning, you cannot produce more species, right? If you have no species. If the humans go extinct, well, there will be no humans anymore. Okay, how about carrying capacity? When population is equal to the carrying capacity, the exact meaning of the carrying capacity is the perfect condition that environment can have. So if you have 100 bears on the park, according to the previous example, you will not have more bears, okay? So the population growth will stop. Okay, so if you have the carrying capacity, the population will not change anymore. Now, based on these facts, how do you think the slope field will look like? Well, think about this scenario. So we have two special scenarios, p is equal to 0 and p is equal to capital K. So when p is equal to 0, well, we will have horizontal slopes. Those are the equilibrium solutions. Rate of change is 0, so we have horizontal slopes. Now, if you have a population less than carrying capacity, what happens? The population will start to increase, right? It will increase and increase and increase up to carrying capacity, then reach the carrying capacity. That's it. Nothing will happen again. Now, if you have a population more than carrying capacities, the species will vanish, die, or not extinct, okay? So the population will decrease and approach carrying capacity and then stabilize there. Nothing will change anymore. So that is how the slope field will look like, okay? And this equilibrium solution, p is equal to k, we call it, is it stable or unstable? Think about it. It's a stable equilibrium solution, right? Because from both sides of the equilibrium solution, the arrows approach towards carrying capacity. Physically, if you have a population just less than carrying capacity, you will increase up to carrying capacity, stabilize. If you have a population over carrying capacity, you will decrease and approach to carrying capacity and then stabilize. So this is an asymptotically stable equilibrium solution. Okay, all right. Now another thing that we are interested is, here's something. So we have this differential equation. When do you think the population growth is fastest? Now think about it. So if you have a population less than carrying capacity, your population is starting to grow, right? We know population growth is not uniform. It's, fast at some times, slow at some times. So what do you think what will happen? Let's do an interesting algebra. Okay, again, let's simplify the right hand side. Let's distribute kp, the brackets. So we will get simple k capital P minus simple k p square over k. This is the right hand side. Let's call it a function of p. We call this the logistic function. Now this function, if you remember from basic calculus, this is a quadratic function of p, right? So quadratic function, how does it look like? If you draw, it's either a maximum parabola or a minimum parabola, right? But if the coefficient in front of the p square term, the square term is negative, then you have a maximum, right? So the parabola, you should have a maximum parabola. And let's find the vertex. Remember vertex, where does the maximum occurs? So the maximum occurs when p is equal to negative b over 2a, right? If you have ap square plus pb bp plus c, the maximum occurs at when p is equal to negative b over 2a. So here the b is simple k, so simple k or negative simple k over 2a, 2 times a is negative simple k over capital K. So now if you simplify this, we can take the reciprocal multiplication of this. Okay, so it's capital K over simple k cancel out and the negative cancel out and become positive. So we get k over 2, capital K over 2. So we have the maximum of this parabola when population is equal to capital K over 2. What does that mean? When the population is exactly half of the carrying capacity, at that time you have a maximum population growth rate. The growth rate is maximum, not the population. Okay, the rate of change the population happens is fast, or the population growth is fastest when the carrying capacity is half. Okay, so our solutions will be like, so you starting to grow. If you have a population less than the half of the carrying capacity, you start to grow and you have a maximum growth rate here, then you slows down and approach carrying capacity. Okay, but if you have a population, initial population bigger than half of the carrying capacity and between the carrying capacity, well, you just slowly increase the population up to carrying capacity, and that's all. But if you have a carrying capacity less than half of the carrying capacity, it will increase very fast at k over 2, and then the rate of change will slow down and approach to carrying capacity. It does make sense physically too, right? So that's the introduction to logistic growth model, and yeah, thank you very much.